Okay everyone, sorry about the different intro to the video. Sorry about this awful watermark down here. This will be the last video I make with that on it, promise. So today we're going to look at existence theorems. It's another one of these videos. I realized I'd never made a video for it. It is part of the curriculum though, kind of a minor part in my opinion. But anyway, for completion's sake, here it is, a video about existence theorems. So we've actually talked about one of these existence theorems before. It was the intermediate value theorem. We discussed that in chapter 1. Go back and look at that one if you want. It's kind of hard to summarize it in less than a few minutes, and I don't want to spend the time right now. So go back and look at that one if you want. So there's three others we're going to look at today: the extreme value theorem, the mean value theorem, and Rolle's theorem. They're all existence theorems, which means they prove something exists. It doesn't actually show you where it exists. So you'll see what I mean when we do this. So let's start with the extreme value theorem. What that says is if a function, f of x, is continuous on the closed interval ab, then f of x has an absolute maximum and an absolute minimum on ab. So can you picture what that means? Let me just draw a couple graphs here. If I draw a continuous function along here, remember that means a function where I don't lift up my pen. So there you go, there's a continuous function. If it's continuous, then there must be an absolute maximum and there must be an absolute minimum. Well, in this case, there's the absolute maximum and there's the absolute minimum. Now you might say, was that always the case? Like, what if I just draw something like, I don't know, something like this? That is a continuous function. Well, guess what? The endpoints, absolute maximum and absolute minimum. Now I know what you're thinking. You're saying there must be an exception, this weird exception. What if it's a constant function? What if it's like, straight across, it's supposed to be straight across, right? Horizontal line. Well, then every point is a maximum and every point is a minimum. Weird, eh? Anyway, there's the extreme value theorem. Okay, the mean value theorem. This is the one that's actually part of the curriculum. So we'll spend a little bit longer for this one. This one says that on the closed interval AB, there exists some point C between A and B such that f prime of C is equal to f of B minus f of A, all divided by B minus A. Okay, now it's kind of a complicated thing, lots of mathematical terms. It's actually pretty cool what this shows us. I'm going to write down here. It shows us that for any closed interval is when you have the square brackets, right? It includes A and B. For any closed interval on a continuous function, so if it's a continuous function, the tangent line will be parallel to the secant line at some point. So here's an example right here. We have this closed interval. We have a function, first of all. The red curve here is a function. It's labeled f of x right here. We have an interval in this function, a to b, and it's continuous from a to b. And what it's saying is there must be some point along here, along this function, where a tangent line drawn at that point is parallel to the secant line drawn between A and B. Does that make sense? I'll kind of go through it one more time here. We have our function, which is red here. We have points A and B, and we draw a secant line that connects them, right? Secant line goes through a curve in two spots, and that's exactly what we have done here. Now, there must be some point on this red curve. I mean, definitely not here, for example. It's not here, because if I draw the tangent line like this, it's definitely not parallel to this highlighted one there. And I don't know, I could do this all over the place, right? If I pick one here, the tangent line is not parallel. And let me do one more. If I pick a point here on the function, the tangent line is not parallel to the highlighted one. But if I was to pick this point, this red point right here, the tangent line is exactly parallel to the secant line. Pretty awesome, right? Now, if we're talking about the slope of this tangent line, remember, parallel means they have the same slope. So if we're talking about the tangent line, the slope of the tangent line, what are we talking about? We're talking about the derivative. Well, that's this piece right here. This is the slope of the tangent. Okay, that's pretty clear. What if we wanted to get the slope of the secant line? How would we do that? Well, to get slope, I'm just going to write it over here. We could use this formula, right? y2 minus y1 over x2 minus x1. I'm actually going to start on the bottom here. The x's are pretty easy. The x's for our secant line are b and a. So for the bottom, it would be b minus a. How about the y values? Well, for this one here, how much is that? I mean, I don't know how much that is. But remember, how you would get that point is put b into the function. You put b into f, you'd get f of b. That would be the y value of the first point minus what would the y value be of this point. You'd put a into the function, f of a. And if you look what I've written right here, do you see it's exactly this right here? In other words, this whole bit right here is the slope of the secant. But wait, there's even more. What's the other definition of the derivative? The other definition is the instantaneous rate of change. Well, what's the other interpretation of the secant line? It's not the instantaneous rate of change, it's the rate of change from A to B. In other words, it's the average rate of change. So there must be some point, also, the other way we could say this for the mean value theorem, there must be some point on the curve where the average rate of change is equal to the instant rate of change at that point. It's pretty cool. Once you wrap your head around it, it's actually a pretty cool idea here. Okay, let's do a question using the mean value theorem. At what x value, or values, on the interval -2, 3, does the graph of f of x equals x squared plus 2x minus 1 satisfy the mean value theorem? Okay, so see this purple bit up here? We got to do both sides of this and see if they're when they equal each other. Well, let's start with the right-hand side, that f of b minus f of a over b minus a. So here's my a, and here's my b. Let's start by actually finding f of b, in other words f of 3, and f of a, which is f of -2. So we're just going to plug 3 into all the x's here. 3 squared is 9, plus 2 times 3 is 6, and then minus 1 equals 14. And for f of -2, we put -2 in here, we square the whole thing. -2 squared is +4. 2 times -2 is -4, and then we still have this -1. So 4 take away 4 is 0, take away another 1 is -1. So if we're interested in the average rate of change, which is the same as the slope of the secant, what we would be doing is f of b minus f of a, well, that's 14, take away -1, and then the denominator, if you look back up here, we just have b minus a. So that would be 3 minus -2. So that gives you 15 over 5, which is equal to 3. Now, if we don't want the average rate of change, but we want the instantaneous rate of change, which is the same as the slope of the, not the secant this time, but the tangent, how do we do that? We take the derivative of f. And the derivative is what? 2x plus 2. So what the mean value theorem says is that at some point the average rate of change, or the slope of the secant, which is equal to 3, must be equal to the instantaneous rate of change, which is the same as the slope of the tangent, which is 2x plus 2. So the final thing you need to do in the question is see, when is that? When is it that 2x plus 2 equals 3? Well, that's no problem. Take away 2 from both sides, and you get 2x equals 1. Divide by 2, and you get x equals 1/2. When x is equal to 1/2, if you were to draw a tangent there, it would be exactly the same slope as the secant line. The secant line that you draw between -2 and 3, of course. Okay? Let's try another one of those. So we're going to start off with the average rate of change. So how do we do that again? Well, here's our a, and here's our b. We need to figure out what g of 1 is this time, and g of 1/4. So put 1 in there. 1 over 1 equals 1. Put 1/4 over there. 1 over 1/4, well, when you do 1 over something, it's just reciprocal, so it's just 4. Okay, so when we want to get the average rate of change, or the slope of the secant, we go g of b minus g of a, so that's 1 take away 4, over b minus a, 1 minus 1/4. So 1 minus 4 is -3. 1 minus 1/4 is 3/4. So let's see, we're dividing fractions. Let's make this a fraction, the -3. So you have -3 over 1. division with fractions is the same as multiplying by the reciprocal. Reciprocal of 3 over 4 is 4 over 3. Then you could do some ninja slicing here. You're left with this negative 4 is your answer. So that's the average rate of change. Whoops, sorry, negative 4. That's the average rate of change, or the slope of the secant. Now let's look at the instantaneous rate of change, which is of course equal to the slope of the tangent line. How do we do that? We have to get g prime. So how could we rewrite this? G of x is the same as x to the negative 1. So we can do the derivative of that, can't we? The negative 1 comes down, so we get negative x to the negative 2, which is the same as negative 1 over x squared. And again, the question we have is, when does the average rate of change equal the instantaneous rate of change? When does the slope of the secant equal the slope of the tangent? When will that be? Well, that'll be when negative 4 is equal to negative 1 over x squared. Well, I guess we could dump the negative on both sides, right? Multiply by negative 1 or divide by negative 1 on both sides. And we could also multiply both sides by x squared. So you get 4x squared equals 1. So x squared equals 1 over 4. Last thing we need to do is take the square root. Don't forget, plus or minus. 1 over 4 is a perfect square. So we get two answers, x equals 1/2 and x equals negative 1/2. Should we accept them both? Be careful. Look, we're talking about the interval 1/4 to 1. From 1/4 to 1. The smallest value we're talking about here is 1/4. This second value is below that. So we have to reject this one. I don't know, you could say not in interval or something like that, which means the only x value that we're interested in this case is x equals 1/2. Okay, now we're going to go into Rolle's theorem. I think that's how you pronounce it. I can't remember, to tell the truth, but I'm pretty sure it's Rolle's theorem. So this is actually just a specific case of the mean value theorem. So what this one says is, oh my gosh, if the endpoints of an interval are at the same height on the graph, in other words, if the secant line is horizontal, then somewhere on that interval, the tangent slope will also be 0. Okay, can you picture that one? Let's use our drawing here to help us out. So here's our function. I don't know why they've drawn it dotted, but here's our function right here. And what they're saying is, if the interval, so we're going from a to b, if f of a is equal to f of b, right? F of a equals f of b, and it's absolutely, they're both on the x-axis. They don't have to both be on the x-axis, but in this case they are both on the x-axis, so they're at the same height. Or another way to think of it is, if I drew the secant line that joined those two things, it'd be a perfect horizontal line. If that's the case, then somewhere on the interval, the tangent slope will also be 0. And that makes sense. At this maximum right here, right, there's going to be a tangent slope of 0. So here's kind of a more mathematical way of saying it. For a continuous function, yes, this black function is continuous, with a closed interval ab, yep, a to b, and f of a equals f of b, yes, because of the same height, that means that f of a equals f of b, then there must exist a point c, there's c, that's between a and b, indeed it is, such that the derivative of the function at that point c is equal to 0. Yes, at that point, the slope of the tangent, or the derivative itself, is equal to 0. So the mean value theorem said that there must be a point where secant and tan are equal to each other. Rolle's theorem is a specific case where the secant line and the tangent line both have a slope of 0. Not only are they equal to each other, they're also both specifically 0. Okay, let's find the x-intercepts of this function and then show that the derivative is equal to 0 at some point between the two intercepts. So the first thing we have to do is find the x-intercepts. Well, what's true about x-intercepts? What's true about x-intercepts is their y values are equal to 0. So in other words, f of x, which is essentially y, would have to be equal to 0. So in order to find the x-intercepts, we just need to solve this. How do we solve quadratic equations? We make it equal to 0, perfect, and we factor if possible. And in this case, we can. What if we couldn't? We'd use the quadratic formula. So two numbers that multiply to 2 and add to -3, I guess that'd be what? -2 and -1. Which means x could be equal to 2 or x could be equal to 1. Alright, those are our endpoints. So in order for Rolle's theorem to work, what needs to be true is that f of 2 and f of 1 need to be exactly equal to each other. right? They have to be at the same height on the graph. So let's see, if I put 2 into here, I get 2 squared, which is 4. 3 times 2, or negative 3 times 2 is negative 6, plus 2. And equals 0. Again, it doesn't have to. This means it's right on the x-axis. It doesn't have to be right on the x-axis, but just so happens it is that way again. Then I put 1 in there. 1 squared is 1, minus 3 times 1 is 3, plus 2. 1 minus 3 is negative 2, plus 2 is 0. So they both are on the x-axis. This would, Rolle's theorem would also work if this was 6 and 6, or 9 and 9, or negative 12 and negative 12, or 82.3 and 82.3. As long as they're the same. So let's kind of summarize. So we have points. One point is 2, 0, and another point is 1, 0. And because the y values are the same, I've got therefore and therefore. But because those are the same, somewhere between x equals 1 and x equals 2, the derivative f prime of x must equal 0. Okay, there you go. That's the existence part of it. We're done with Rolle's theorem. But we could actually show you where it is if you wanted to. You want to see where it equals? I've already know it's between 1 and 2, but let's find the actual spot. How do you find where the slope is equal to 0? You take the derivative. We're talking about the slope of a tangent. So let's take the derivative. F prime of x is equal to, what, 2x minus 3? And we want to know, when is the tangent horizontal? When is that equal to 0? Well, easy to solve. Move the negative 3 over, it becomes positive 3. Divide by 2, you get 3 over 2. Or if it helps you picture it, what's that as a decimal? 1.5. Hey, wait a minute, 1.5, that falls between 1 and 2. It doesn't mean it has to be right in the middle either. Maybe a bad example. It doesn't mean it has to be right in the middle. It just means somewhere between 1 and 2, you're going to find that spot. It just happened to be right in the middle this time. So, yep, it actually did work. Rolle's theorem said there would be one between 1 and 2, and we found it. It's right there. Now, what we don't know yet if it's a maximum or a minimum, but it doesn't matter in this case. We're just trying to work with Rolle's theorem a little bit. Okay, that's it. Take care.